All right, guys. So welcome to the first lecture. This is going to be on section 1.4, and it's going to be on separable differential equations. As always, this will be your first video, but as always, I'm going to give you guys the prerequisites that you need for this section. So this will be the first section on differential equations, but in order to do this stuff in this section, you need these are your prerequisites. We're gonna need some algebraic manipulation. Can you move things around an equation, right? Logarithms, exponential properties, moving trig functions around, some maybe some factoring, things like that. And we will also need some integration techniques. Which integration techniques? Well, whatever is necessary for the problem, right? So maybe you'll have to integrate some trig functions, maybe some hyperbolic functions, definitely some exponential functions, things like that. You'll need to know how to integrate by substitution, integrate by parts, things like that. So all the things that you learned in Calculus 2, you will need those things for this particular section. So, without further ado, let's go ahead and jump into this. What is a separable differential equation? Well, honestly, it's any differential equation which can be written as some function of y times y prime, or dy dx, is equal to some other function of x. That's it. Okay. So what we notice is, ignore the differential for the moment. What we have on the left is nothing but y's, and on the right we have nothing but x's, hence the term separable. We have separated the y's from the x's. Now, we don't actually want this form. The key, however, is that if you can get it into this form, then this is equivalent to this one. So some function of y times the differential of y, and that's equal to some other function of x times the differential of x. Okay, and this is what we really want, right? I want this, because if I can get it in this form, then doing something just as simple as integrating both sides actually makes sense, right? At this point in time, I'll be integrating a function in y with respect to y. I'll be integrating a function in x with respect to x. And at that point in time, hopefully the result of these integrations will give me something which will give me a general solution for my differential equation. Now, again, where the hiccup's going to come, well, one, it's not going to be separated for you. You're going to have to separate it yourself, right? And so some of those, some are easy, some are a little bit less so. You'll have to be a little bit more creative or clever when you're doing it. And I'm not going to lie to you, most of my students struggle with the integration part. Man, go back, review integration, right? Review integration, review integration. You're going to need to be able to integrate anything you come across. Anything from Calculus 2 or before, it's all fair game. Okay? All right, so because I'm certain that you guys probably like to learn from examples, let me go ahead and get one up here. Okay, let me go ahead and get one up here that we can work from. And I like this example because it illustrates a few different things that might happen, so a few different possible snafus. And on the surface, the example looks very, very simple, right? It's y prime is equal to, we've got negative 2x y squared. That's it. Okay? Okay, so again, what we've got here, we have our differential equation. This is dy dx. I've got some x's and some y's, and they're not separated, so I will need to actually separate them myself, and that's not a huge deal. Okay? What I can do is I can take my my y squared here, I can move this to the left, giving me y to the negative 2 times y prime, and that's equal to negative 2x. And I'm going to put an asterisk next to this step because we're going to have to come back to this in a minute. Okay, so just duly noted, I have to come back to that in a second. Okay? Okay, so, but for right now, this is the form we were looking for, right? This is some function of y, dy dx is equal to some function of x. And what I mentioned was, what we really want is, we really want to rewrite this as some function of y times the differential of y, and that's equal to some function of x times the differential of x. Okay? And again, theoretically, we can just integrate both of these sides. It's not a problem. There we go. Okay, so we can integrate the left, we can integrate the right. Let's see, the integral of y to the negative 2. This is a simple power rule. So this gives me negative y to the negative 1. All right, you know what, plus c, but I'm going to come back to this in a second. Okay, again, integrating the right side, I've got negative 2x. That integrates fairly easily just into negative x squared. And again, I need to add a constant. Now the problem is, are these two constants the same? Well, not necessarily, right? And so I've got two choices. The heavy-handed approach is to call this one C1 and that one C2, but I don't want to do that, and I don't have to. Because if this is some arbitrary constant and that is some other arbitrary constant, couldn't I just lump them together and call it one arbitrary constant? I mean, for example, if this came out to be 3, that came out to be 7, couldn't I just subtract the 3 over there and just call that a 4? Yeah? And so in general, even if you integrate both sides of your equation, you just need the one arbitrary constant, right? Yeah, and that also saves me from having to use any unnecessary indices here. Okay, so again, technically I get a constant on both sides, but I'm going to lump all those together on the right. Okay, okay, so this is not that bad. Let me go ahead and multiply both sides by negative 1, giving me y to the negative 1 is equal to x squared. I'm going to write plus c. Again, distributing a negative 1 here, you get positive x squared minus c, but that's an arbitrary constant, right? So plus, minus, whatever. Okay, and now I'll just take a reciprocal. Okay, 1 over y is technically y to the negative 1, so I'll take a reciprocal of both sides of my equation. Okay, and I get y is equal to 1 over x squared plus c. Okay, and this is wrong. Or I should say it's incomplete. Right? So this is supposed to, as a general solution, this is supposed to represent all of the possible solutions for our differential equation. The problem is it just doesn't, right? For example, is this function a solution? So is y equals 0, the function, that's not a number, that's the function y equals 0, a solution. Okay? Okay? And again, remember what this looks like. Y, this solution here, this is an entire function, yes? So specifically, y equals 0 is the horizontal line along the x-axis. So is that line a solution for this? Well, I don't know. Let's plug it in, right? So if y is equal to 0, then y prime also equal to 0, yes? Derivative of 0 is 0. Let's plug that in here. And if I plug that in, I get 0 is equal to negative 2x times 0 squared. Now, of course, this would have to be true for every possible value of x, but I think it is, right? 0 squared 0, 0 times negative 2x is 0 for every possible value of x. So yeah, this checks out. Yeah, so 0 is equal to 0. Okay, fine. But what that tells me that y equals 0 is actually a solution here. Now, let's go back down to my general solution. Can you make y equals 0 from this? Well, no. You can't get 0. You cannot get the eidetic function y equals 0. This is a fraction, and the numerator is 1. No fraction with a numerator of 1 equals 0. So we have a problem here. This is a solution, but it's not actually generated from my solving. And so how did this happen, right? We didn't technically do anything wrong, right? How did somehow we come up with a general solution here that doesn't actually include all the solutions? Well, it goes back to this step I put an asterisk by, right? Okay. What we notice for this asterisk step is how exactly did we get here? Well, technically speaking, what we did was we took y prime is equal to negative 2x y squared, and really we divided both sides by y squared, right? And that's again, it's easier to use negative exponents. That's really what we did. And the problem is that particular step is not valid if y is equal to 0. Okay? If y is equal to 0, this step is not appropriate. Okay? Because of course you can't divide by 0. So the problem is with my first algebraic step here, I need to make a note, right? And this is going to happen. You need to be aware of this whenever you're separating your equations, whenever you're separating them. You might end up dividing by something that may end up excluding a solution. So here I have to note and ask myself, does y equal 0? Because remember, dividing here, that's the one I'm excluding. Does y equal 0 serve as a solution? Okay? Because my algebra for the rest of this, okay, is going to give me all the solutions other than y equals 0. Now, again, not every time you do this will you actually exclude a solution, right? It's entirely possible that you end up excluding, let's say, something silly like y equals 3, and at the end, well, y equals 3 was never a solution to start with, so we don't have to worry about it, right? I'm just telling you, you need to check, right? You always need to check. So the question then becomes, what actually is my solution? Well, it turns out that I just have to add that on. So I'll accept this as a... This is not formally written, but that's a perfectly acceptable way to write your solutions as far as I'm concerned. Okay? All right, so this is the general strategy by which you're going to solve all of your separable differential equations, but you need to be aware that if you exclude something, right, if you divide by some unknown value, you got to be aware that you may have excluded a solution. You got to go back and check those things. Okay? All right, fantastic. So now let's do a slightly more interesting example. I'm going to do one that's a little bit more interesting, if only because some of the algebra in this one catches my students every semester. So let me work this one out, just because I'd rather you guys have an example on record. So let's say we have 3 to the 2x plus y power dy is equal to 4 dx. Okay, so again, this is separable. I need to figure out actually how to separate it though, but separating this should be actually fairly easy. How do I separate the exponent, right? Both the x and the y are in that exponent. And we can think about it in terms of something like, well, what's x squared times x cubed? Well, it's x to the 5th, right? But again, the property for multiplying like bases is that I add the exponents, for x to the 2 plus 3. Okay? Well, that's what I have here, right? I have exponents which are summed together. So what I can do is, I can just use that same property, but I'm going to use it in the other direction. So this is the same as 3 to the 2x times 3 to the y. Okay? Fantastic. And now I'd like all of my x's on that left-hand side. So let me go ahead and divide both sides by 3 to the 2x, or multiply by 3 to the negative 2x. Okay. Now again, this was that division step, right? Yes? Okay, that was that division step. Did I just preclude some of my answers? Well, what did I divide by? I divided by 3 to the 2x. And that's only valid as long as 3 to the 2x is not 0. I claim that's not an issue. I'm not going to tell you why. Think about it. Why is 3 to the 2x being 0 not a problem? Okay. Let's see if we can finish this. We're just going to integrate both sides. Fine. So there we go. Let's integrate the left, integrate the right. Okay. And how do we integrate 3 to the y? Well, it's pretty easy. Okay. The integral of 3 to the y is 1 over the natural log of 3 times 3 to the y. Okay. Again, technically plus c, but yeah, whatever. Okay. Again, where am I getting this? Remember, you have your basic derivative rules here. That the derivative of a to the x power is the natural log of a times a to the x power. So remember, the natural log of a, that's just a constant, right? So again, if I'm integrating, this is my adjustment constant. So again, if I take a derivative here, the natural log of 3's would cancel, which is what I'm looking for. Same principle here. So again, I'm just integrating this particular part, and this is a substitution, right? So I've got a negative 2x up here. Okay, so again, integrating, we'll have to integrate by substitution. I'm going to skip through this. Again, if you want a deeper explanation for integration by substitution, ask me in one of our actual sessions. Okay, I'll actually write out the pieces though. So I've got 4 times. So again, the integration here is 1 over the natural log of 3, and I'm also going to get negative 1/2 from my substitution, and then again times 3 to the negative 2x, and I'll actually put my plus c right here. So cleaning all these things up, on the left-hand side, I'm going to have 3 to the y. On the right-hand side, 4 times negative 1/2 is negative 2. And I can take this 1 over natural log of 3 and this 1 over natural log of 3, and I can throw those away. I can multiply both sides by natural log of 3, which gives me just this. All right. That's not terrible. We're not quite done, though. I haven't actually isolated my y. And how can I do that? Well, I've got a few ways. I can use, so I'm going to use a logarithm, but I can use any base logarithm I'd like. I can use log base 3. We're going to use the natural log. And the reason we're going to use the natural log is it's just the nicest logarithm when it comes to calculus, integration, derivatives, things like that. So let me go ahead and take the natural log of both sides. So I've got the natural log of 3 to the y. And over here on the right, I've got the natural log of negative 2 times 3 to the negative 2x plus c. And it's at this point that, man, I have some students that start getting all kinds of crazy with their attempted simplifications here. So to be clear, the natural log does not distribute, so there's really nothing you can do with this. Okay, you can't multiply the negative 2 and the 3 together. Please don't try. Okay, In fact, the only reason why I did this is that for the left-hand side, I can rewrite that exponent as a coefficient. That gives me y times natural log of 3 is equal to the natural log of negative 2 times 3 to the negative 2x plus c. There we go. So just divide by natural log of 3. This is just a constant, so it's not a big deal. And so I get y is equal to 1 over the natural log of 3 times the natural log of negative 2 times 3 to the negative 2x plus c. All right, not terrible, right? And again, for our division step earlier, we did check, right? We did check that did not actually preclude any solutions. So here's my general solution, right? This constitutes all the possible solutions for that particular differential equation. Okay? All right. So this is not overly terrible, I hope. And I know what you're thinking. You're thinking, man, I really wish we could use this in a word problem. Okay, if you insist, we will. We can use it in a word problem. One of the things that separable differential equations model very nicely are heating and cooling problems. Specifically, Newton's law of heating and cooling. Okay, I'm going to put that up in a second. Let me get this problem up here first. The problem says a 350 degree Fahrenheit for some godforsaken. I'm using the one out of your book. It's just not using the metric system for some reason. Okay, metal bar is placed in a room whose temperature is constant at 70 degrees. Room. Gotta put those two words very close together. Held at a constant .70 Fahrenheit. Fantastic. Okay. After 2 minutes, the temperature of the bar is 210 degrees Fahrenheit. Okay. After 2 minutes, bar is 210 degrees Fahrenheit. Okay. So using Newton's law of cooling, blah, blah, blah. You know, it asks you some questions after this, but I'm not actually going to put the questions up there because these word problems we're going to deal with, they're going to come in basically 2 stages. I'm going to get the problem, and the first thing I need to do is I need to actually model the problem, and then it's going to ask me questions about the model, right? It's going to ask me things like, find the temperature of the bar after 4 minutes, right? Find the time required for the bar to cool to 100 degrees Fahrenheit. But if I can just come up with a model to represent the temperature at any time t, then these questions are trivial, right? They're just me plugging in values to an equation, and we can easily do that on our calculator. So the question then becomes, what the hell is Newton's law of cooling? Okay, well, all right, so for those of you that haven't taken your physics class relevant to this yet, the quick rundown is that Newton's law of cooling says that heat is exchanged between 2 states at a rate relative to their difference in temperature. So let me explain that in somewhat more relevant terms, right? Let's say you take a cake and you take it out of the oven. Let's say you baked it at 350 degrees, right? So you got a cake, you take it out of the oven, and it's too hot right now, right? So if you put it just on your counter, it's going to cool down eventually, yes? would it cool down faster or slower if you put it in your freezer? Well, obviously it would cool down faster if you put it in your freezer, right? And the difference is your house is around 70 degrees, giving you a difference in temperature of about 280 degrees to start with, whereas your freezer is around 30 degrees, giving you a 320 degree difference, right? The larger the difference in relative temperatures, the quicker the heat transfer, okay? So what that means is that initially this bar is going to start cooling down very, very quickly, okay? But the lower the temperature gets, the closer the bar's temperature gets to 70 degrees, the slower it's going to lose heat. And we need to represent that with an equation. And the equation is very simple. The rate at which the temperature is changing is directly proportional to the difference in temperatures. So let's see if we can't write that down. Okay, so the rate, that would be d temperature d time. This is the change in temperature with respect to time, so it's the rate at which the temperature is changing. Okay, is directly proportional to, that means is equivalent to a constant times something. This constant, depending on which textbook you're looking in, is either written as k or negative k. It doesn't matter, okay? If you write k and k comes out to be 400, then k is 400. If you wrote negative k and then k is 400, then it would be negative 400 constant, right? It's fine, okay? The math will take care of the positive and negative sign, so I write positive because it saves ink, right? All right, so the change in the temperature is directly proportional to the difference in the temperatures. So difference in the temperatures here, we have to model. We're going to put the temperature of the bar minus the ambient temperature. Now I'm using the same variables as your book does, but these things I feel are somewhat poorly labeled. Okay, so again, T here we have, this is the temperature of the bar. Okay, so this is a variable. The bar is cooling down. It changes periodically. Okay, this is the ambient temperature of the room in this case. Okay, and this, it very specifically says, is constant, right? So this is not a variable. Okay, you could work these types of problems where both of these things are variable, but that's a little bit more complicated than what we're going to do this semester. So here's my model, right? My model is dt dt is equal to k times t minus t sub n. So what do I know about this? Well, honestly, the only thing I know from this model is t sub n. Okay, I know that one's 70. So I'm going to erase this. I'm going to rewrite it with what I know. I know t sub n is 70. Okay, we'll try to see if we can look through the problem and glean a little bit more information here, right? So let's write down, so here's my starting model, okay, dt dt, that's equal to k times t minus t sub m, okay? All right, and then from my problem here, I know, okay, t sub m, 70. I got that part, that's in there. Okay. Now what else? What else? Well, I know the temperature of the bar when we start, right? It says a 350 degree metal bar. And if I'm trying to write temperature as a function of time, then it'll be the temperature at time 0, so T of T, right? This is going to be temperature as a function of little t time, and at time 0, I know this temperature is 350 degrees. And then using that same logic, it says after 2 minutes the bar is 210 degrees. So let me just write that down here. So T of 2, that's got to be 210. Okay, so these are all the things that I know. Okay, so here's all the information I know, and here's my model. Now again, let's remember what we want. What we want is a function where I can plug in a time and it will spit out a temperature, right? That's what I really want. I can use that to answer any of these questions. So let me see if I can go ahead and do that. What we have right now, the only thing we know for certain is that my model is dt is equal to k times t minus 70. Well, yeah, but I can't use these two pieces of information until I actually get my model. But this is separable. Okay. All right. So let me go ahead and see if I can rearrange this a bit. Let me divide by t minus 70. Okay. Now I want to talk about something for a second. I'm gonna rewrite this in my separated form, right? So I just divided by t minus 70, and that's only going to be a problem if the temperature, capital T, ever hits 70 degrees. Now the temperature, that capital T, that's the temperature of the bar, will the temperature of the bar ever actually hit 70 degrees? In real life, yes, yeah, it will, right? Because in real life, things are discrete. There is no continuum. But my model is not. My model is continuous. This model will run forever, and that temperature will never get, this value here, T, will never actually get to 70 degrees. Okay? But again, that's a difference between our mathematical modeling and real life. So this is fine. I've divided by something that can't actually be zero for the purposes of my model, so I don't have to worry about it. Let me go ahead and integrate both sides now. Okay? All right. All right. So integral of 1 over t minus 70, that's just the natural log of t minus 70. Technically speaking, it's the absolute value, right? Okay, but I'm going to use some parentheses. I claim we don't actually need the absolute values here. Okay, why don't we need the absolute values? Well, not only can this not be 70, isn't the temperature of the bar always going to be larger than 70, right? If it's cooling down towards 70 degrees. So if this value is always larger than 70 and you subtract 70, then this value is positive and I don't need absolute value, right? Okay. Integral on the right-hand side, k is just a constant. Integral of a constant is k times t plus c. It's a random constant. And then I can solve for my temperature here by exponentiating both sides. I'll take both sides. I'll raise e to the natural log t minus 70. On the right-hand side, e to the k t plus c. Left-hand side's pretty easy. That's just t minus 70. Okay. Some interesting simplification on the right-hand side. Remember that same exponential trick we used for the previous problem, right? I've got a sum of exponents here. And if I wanted to, I can rewrite that as a product of bases. So that gives me e to the k t times e to the c. Now, why did I want to do this? Well, e is a constant. So is c. C is also a constant. So you have some constant raised to another arbitrary constant. I'm just going to replace that with another arbitrary constant, right? So this gives me t minus 70 is equal to some constant times e to the kt. Now, obviously, to solve for my temperature, all I got to do is add 70 over there, right? Okay. So that's going to give me, I finally have a model I can work with here. That's going to give me my temperature is equal to c times e to the kt plus 70. Okay? And this is my temperature. Again, I left a space here. I'm writing this as a function. This temperature is a function of time. This is really t of t, right? This is the temperature as a function of time. Fair enough. Now that I have this, what I realize is that this model is not actually useful. It doesn't actually do what I want it to. I'd like to be able to plug in a temperature, time rather, and get temperature. The problem is I don't know K and I don't know C. I need to know these two things in order for this model to actually work. So, okay, fine. How do I find K and C? Well, that's what this extra information is for, right? what I have here is that I know that t of 0 is 350. Well, let's plug that in. So I plug in t of 0, that's c times e to the k times 0 plus 70. So t of 0, left-hand side, that's 350. I know that's right. Well, k times 0 is 0, right? Yeah? So this is c times e to the 0, but e to the 0 is 1. So I get 350 is equal to c plus 70. That's pretty nice. Subtract over 70, and I get 280 is equal to c. Okay, all right, that's useful. Yeah. Because that tells me my model can be updated here, right? Yeah. My model actually reads instead of c times e to the kt, it's 280 times e to the kt. Okay. Oh, that's a much better model now, right? Still not functional. Still not functional. If I plug in t, unfortunately, I still don't know what k is. But again, that's why I have another piece of information, right? So now let's try my second piece of information here and see what that one will give me. So let's see. So what other piece of information is that t of 2 is 210. Okay, again, let's go ahead and plug these things in. So I get t of 2 is equal to 280 times e to the k times 2 plus 70. T to the 2 is 210. Okay. And this equation just has one unknown in it. That's k, and so we can solve. Again, this is just from basic algebra. We'll subtract over the 70. We get 140. Divide both sides by 280. So we get 1/2 is equal to e to the k times 2. Take the natural log of both sides. I get the natural log of 1/2 is equal to k times 2. And I can just divide both sides by 2, giving me k is equal to the natural log of 1/2 over 2. And anything equivalent to this is fine as well. You can write negative natural log of 2 over 2. It's the same expression. Okay. But what this does is that this finally fixes my model, right? Yeah, this finally fixes my model. Okay. Because instead of it being e to the kt, I know what k is, right? K is the natural log of 1/2 over 2. Please do not type this into your calculator. If you type natural log of 1/2 over 2 into your calculator, you're going to get a very, very awful decimal that you're going to have to round. Don't round now. In fact, I don't even want you to round ever. But again, don't round early. You never want to use a rounded answer to get another rounded answer. Every time you round something, the answer you have is wrong, and you make it more wrong by using that to find other answers and then round those. Okay? So again, there's my model. Okay? And all this work was done for what? Well, this problem continued, right? The next part of the problem says, so part 1, find the temperature of the bar after 4 minutes. Well, yeah, but that's what this model's for, right? You just, I don't know, plug in 4. Okay? So what's t of 4? I don't know, plug it in. 280 times e is the natural log of 1/2 over 2 times 4 plus 70. And again, you can mash that into your calculator, I don't know, do whatever the hell you want. To be perfectly honest, it comes out to 140, so There you go. Okay. It actually comes out very, very nice. So it's not actually a decimal. Again, there's another question. What is it? How long? Yeah. Find the time required for the bar to cool down to 100 degrees. Okay. So find time required for the bar to cool to 100 degrees. And again, that's just giving you the other variable, right? If you want the temperature to be 100, then again, plug that in. You'll get 100 is equal to 280 times e to the natural log 1/2 over 2 times t plus 70. And again, there's only one variable in this, right? So you can just solve for t. I'm not going to go, that one's not very nice, so I can't do it in my head. But okay. Yeah. So here's a nice application for your separable differential equation. Okay. All right, guys. So this is it for the separable differential equations lecture. I'm going to post the homework online, but actually I haven't spoken to you guys yet on the first day of class. So I'll wait till after that happens. But I'll post the homework online, and I'll talk to you a little bit more in our actual Zoom meeting about the homework, how you guys will turn that in, and how the rest of the class will work. Okay. All right. Bye.